Howdy, y'all. My name is Matt Oztalay. I am a senior technical artist on the developer relations team here at Epic Games, and today I have for you a literal fever dream that I had about using Niagara to represent and interact with the units of a real-time strategy game, and I decided to do it on a phone as a little added challenge. So let's take a look at what I've got. So what I've got here are about 4,000 units, and you can see they're all little flipbook sprites. But I've got like the little health of the units. I've got all these different units here, and I can come over here. I can select these units. I can tell them where to move. And these are all, it's just one Niagara particle system, right? And you can even see that the units are kind of getting out of each other's way and trying to go where they're supposed to go. And of course, we've got a little fog of war effect going on in the corner, right? So pretty cool, a lot of fun. And I wanted to talk about this in the context of a real-time strategy game because there are a lot of challenges in a real-time strategy game that are difficult to overcome using some of the built-in sort of normal pathways you might take in the Unreal Engine. We've got a bunch of things that are all relevant to each other, all relevant to gameplay, need to be interacted with, need to be kept track of. And the thing is, you shouldn't use just characters to do this, right? The A character base class with a skeletal mesh and a bunch of bones and a collision capsule and navigation, it's not necessarily the right choice for this specific application. So we need a system that can efficiently represent the units, allow interaction with the units and the units to interact with each other, store information about those units, and share information about those units with other systems in the engine so we can do some cool stuff with them, right? Now, there is a system for this in the Unreal Engine. Does anybody know what it's called? Raise your hand. Yeah, you in the back. What's it called?
Data channel?
Wrong. It's called Mass. Mass Entity is a framework for data-oriented calculations using entities, fragments, and archetypes. Mass Gameplay is a plugin that builds on that includes functionality for world representation, spawning, lotting, replication, even state tree. There's also Mass Avoidance, which uses forces to get all of your entities to avoid each other. It's really, really cool. And the thing is, Mass is objectively, in my opinion, the right system to use to build a real-time strategy game. But I am a tech artist, and that sign can't stop me because I can't read. So strap in. Because really, to me, this talk is about bringing the fire of graphics programming to the tech artist. And if I suffer avian consequences for it, then so be it. So what are we actually going to learn today? Like I said, there are interesting challenges with the real-time strategy genre. It gives me a really easy framing to introduce to you some really powerful tools and techniques with much broader applications in a cohesive way. So we're going to learn how we can use Niagara as a compute shader to represent and drive the logic of our units both on the CPU and the GPU. And while we're in Niagara land, we'll get a quick example of how to use neighbor grid 3D so our units can avoid each other. And we're also going to learn how we can pack a lot of information into a single float. And finally, we'll use the information from the Niagara system to draw a distance field for the fog of war effect. Ready to roll? Cool. All right, so let's talk about compute shaders. You've probably heard something, I've probably even said this to you, that Niagara is basically a compute shader. And compute shaders are basically a shading stage used for computing arbitrary information, not meant necessarily for drawing pixels or triangles. And all it really is we're taking inputs from the CPU, handing it off to the GPU, said, hey, can you run some math on this? And then we can get the results back onto the CPU, right? Optionally. So we're going to start in Niagara, of course. I've already done a little bit of setup because I know this demo is going to be a little tight for time. But basically what I've got here is a GPU sim particle with fixed bounds already set. I've got a bunch of user parameters. So what we're going to do in our little demo today is not the full thing that you saw. Again, tight for time. But we're going to take our little particles. We're going to give them random goal positions that they're supposed to move to based on relative to where they are. So instead of just constantly bouncing around the screen, it's to say, okay, you only move 500 units away from where you are. So we've got an input vector array of goal positions that is set to sync CPU to GPU. We've also got another user parameter here called out positions, and this is sync GPU to CPU. So we're going to write the position of the particle into this array from the emitter and then read that back in Blueprint. And just as a little pro tip, definitely set the max elements on that, otherwise this won't work. So that's all of our setup, and then I hit Windows D, because I'm really good at my job. There we go. There we go. And then I've also got a texture render target user parameter down here that is set to RGBA32F because we want to have 32 bits of precision for this. And then, so I've set that emitter property over here so everything links up nicely. I've also got a module here that basically initializes the size of the render target and the size of the output array to match the size of the input array. So this is going to be our kind of source of truth. And then down here, I'm spawning particles in a grid because I didn't want them to collide with each other right off the hop. And I think that's all I've got. And we can start getting into it. So the first thing we're going to do in our particle update, we're going to create a new scratchpad module, which we will name move units toward goal. And we need a few inputs to this. One of them is our vector array. And another is the unique ID. The thing I forgot to mention is that this particle system, this emitter is set to requires persistent IDs because the thing that matters, the thing that identifies this particle between both systems is the index in the array. So the 0th particle is the 0 index in the array, is the 0 position in the render target. We can associate all those things together. So we use unique ID, not execution index. And then finally, we need the current particle position because we're gonna push it toward that location. So I'm gonna grab the vector array and I'm gonna say get a value off this vector array. And then I'm going to grab the position value. I'm going to say truncate, please. And then I'm going to convert that to a vector so we can just operate in that space. And then in order to get the direction from the current position to the goal, we just do a little subtraction. And then finally, I'm going to multiply this by an optional scalar value, which I just conveniently convert to a float and drag that on as an input, which we're just going to leave named as is. And then we're going to set a vector value on the output here, which we're going to call physics force, which is in the transient namespace. And so this is going to say, hey, this is how much force is currently applied to this particle. And then what's really nice about this is that that's then going to get picked up by this solve forces and velocities node, right? I'm just telling the forces and velocities solver, here's how much force we have to work with, okay? And then I always have to make sure that I link my inputs. So we're going to start with the goal positions. And then I'm going to set the magnitude to 1. And you can see the particles are going to start moving. So they kind of swapped positions because they didn't get spawned in their right spot. Then I can go over into the goal positions array because I've got this set up as debug. And I can say, hey, you're actually supposed to move much farther away from each other. So little bit of debug there, but you can see, everything's working. I've got these little sprites moving around. And then next up, we're going to jump into the blueprint. Oh, next up, we're going to finalize the particles because the blueprint needs to know where these particles are. And to do that, I'm going to set up another simulation stage. And all this really is like, hey, I've got a thing in the emitter and I need to iterate over a bunch of things. And the default iteration source is particles, but you could also do something like a grid 2D or even a grid 3D, links at the end of the show. And in this one, so it's like, all right, now that we've done all of our particle updates, now we're going to reiterate over all the particles now that we know where they actually are. So I can create another scratchpad module, which is we're going to call finalize units. And same thing, we need a vector array input, but this is going to be the output array that we're going to be writing to. And we also need the render target data interface that we're going to work with. And then, of course, the unique ID. So then I can just set the array element over here to the particle position. There we go. And I'm going to convert that to a vector just the way it is. Totally fine. Actually, I want to truncate that because I bet I'm going to get a warning if I don't do this right. Convert numeric to vector. There we go. And then we make sure that we set that unique ID over there, plug everything in, and then we're going to because we're going to set a value on the render target, so set render target value. And then you notice I've got X and Y index, and we all know that there's a certain amount of math that we could do to get this correct, but luckily we can just do a linear to index so that I don't have to remember all that math on the fly because there's a lot to cover. And then finally, we're just going to set the value in the render target. So now we've got a render target that knows where the particle is, and we've got the CPU is going to know where the particle is. We're going to do stuff with the render target later. It'll be really cool, trust me. All right, so that's the setup on the Niagara side. Now we're going to jump over to the blueprint. I've already got some of this stuff staged already. So you can see I've got a certain number of particles. I resize the array accordingly because this is the thing that's going to tell the particle system how many particles to spawn. And then I'll grab my Niagara system component, and I'll say set array, set vector array. There we go, and plug everything in. And then when I was setting all of this up on the blueprint side of things, I called everything goal locations. And on the Niagara side, I called it goal positions. And for that, I will burn, and I apologize. And then we're going to set active on the emitter because all of that initialization is happening on spawn. So I set it to not auto-activate until we actually get the values in the right spot. And then I've got this set timer by event over here. And so every 3 seconds, we're going to trigger this function, which is going to get the values from the Niagara system. So we're going to get vector array, and that will be our out positions. And then we're going to iterate over this array because, again, the 0 array in the goal position, the zero position in the out position, so those are the same particle. So then I can know where that particle currently is, and then I can set a new goal location for it relative to its current position. So we can drop that in there. And then I had to remind myself because every time I did this demo, I forgot this part and I wondered why it didn't work. So then we have to do the set array vector again to wrap everything up. So that'll be the goal positions, and we can update everything accordingly. Yep. Okay, so fingers crossed. Yeah, all right, so I've got 64 particles. They're moving toward the center, and now you can see they're starting to spread out. They're gonna go start randomizing their locations. And because I didn't think that was far enough away from everything, I'm gonna set that max distance away to something like 500. There we go. So I jump back in, play in editor. So 3 seconds, and then we're gonna start scattering around. So because I know where the particles currently are, I can tell them to go somewhere else. And they all went out in a circle because that was, they all started from 0, 0, 0. But maybe I actually want these particles to kind of bump into each other. And we'll get to that in a second. So again, this is basically what's happening with my RTS here, is I've got all these units and I know their locations in the world. I can project that to screen space, and I know this my little marquee selection box. So anything inside that box, I say, hey, you're selected. And then when I double click, if you're selected, I update your goal location and send that back onto Niagara. Super easy. So that's basically it, right? We tell the GPU to do some work for us on data that we've provided from the CPU, and then we can get Niagara to give us the results back. Pretty straightforward to me. But I want those units I want my sprites to kind of bump into each other. I don't want it to just be, going straight to where they're supposed to go. And the thing that you don't want to do is this. For each particle, go over every other particle, calculate the distance to it to figure out what its relevance is, and check the distances between, because then that's another square root operator, which is super expensive. And the reason that this doesn't really work is that the complexity of this calculation will increase with the number of particles. So 10 particles, totally fine. 100 particles, you're already in deep trouble. Luckily, we have something for that. It's called Neighbor Grid 3D. And it's basically a giant grid with different grid cells based on your parameters. And it's storing the index of the particle in that grid unit to say, okay, if I'm in 0, 0, 0, I've got particles 2, 10, and 12. And that makes it really easy to access, and we can do other stuff with this. And it also means we can bound our calculation to the 27 grid cells around us. So the 9 on the bottom, the 9 in the middle, the 9 above, and it caps the number of neighbors that we're going to have to iterate over so that we can, again, keep the complexity of this calculation a little lower. So we're going to jump back into Niagara here, and we're going to get this set up. So I didn't want to stage all of this stuff to begin with, so bear with me while I create our emitter properties. So the two things that we're going to need here are a Neighbor Grid 3D, and we're going to need a attribute reader, a particle attribute reader. And this is sort of the data interface we will use so that when we're working on one particle, we can figure out where the other particle is. And then to get that set up, easy to set up the attribute reader, we just drag it over and say, hey, this is the emitter that we're working on. We are working on ourselves. And then we need to initialize the Neighbor Grid 3D which luckily comes in a handy dandy module, but it is not in the library, so you got to turn off library only. So initialize grid 3D. And then I'm going to set that to, like 5,000 units, 5,000 units. Pro tip, if you set the local pivot to 0, 0, 0, and your particles are starting in the bottom corner, things will get a little weird. Don't ask me how I know. And then I'm going to, just for the sake of argument, I'm going to set the max neighbors per cell to 15, and then I'll set my the number of cells in any given direction to 15 as well. But you would want to customize these to suit your needs, and these numbers don't actually work because I'm doing everything on the XY plane. But for the sake of argument, we're going to do it that way. All right, so next, initialize grid. Oh, and then I have to set the emitter property that I set up earlier, this neighbor grid 3D, to the output of initialize neighbor grid. Otherwise, things will go a little skew-with. There we go. Okay, so I've got the particles, and I know where they are after I've done the initial solve forces and velocities. Great. Now I need to iterate over all of those particles again to store their indices in the neighbor grid 3D. So I'm going to do that with another. I'm going to do that with another simulation stage, which we're going to call populate for the sake of time. And then we'll add a new module, which is the populate neighbor grid module. Easy peasy. This takes a couple of inputs. It's just our neighbor grid 3D. There we go. It's already set up to grab the particle position. And then we need the world grid, world, come on. Oh, there we go. World to grid unit matrix. And this is going to help everything transform into the right space. So that's going to put up to the max number of particles we've decided into the neighbor grid 3D. And then we're going to get another simulation stage going, and this is where we're going to do our avoidance. So that's another grid, another value, and we're going to need two modules in here. And first we need solve forces and velocities again, because we're going to push the units away from each other. And then we need a scratch pad module, which we will call avoidance. And this is going to look a little scary, but it's okay. We're going to walk everybody through it. Ready? It's fine. It's fine. It's actually, this is a stripped down version of something that we've got in our content examples, so definitely check that out. But what I've got here is sort of the core logic of our avoidance. And while I set up the inputs on this module, if you'll bear with me for just a second. So I need the unique index. Plug that into the instance index, random unit vector. While I was working on this demo, I realized that there was this weird issue where the particles, if they were directly on top of each other, would explode away from each other. So if they're really close together, I just kind of offset that position as a little wink and a nudge. There we go, we plug that bad boy in. And then our output value here, again, it's a force, so we're gonna say, hey, the output here is this transient physics force value. Change namespace to transient. There we go. All right, I'm going to walk you through this, and I'm going to zoom in real good. So up at the top here, all we're doing is initializing our output parameters. So our repulsive force, how much we're going to push everybody away. And then I've got this array of instance index offsets. So if the bottom left corner of the 27 grids that we're going to work with, that's -1, -1, -1, and the top right is +1, +1, +1. I'm just storing all these in a flat array to make things a little easier on myself. Don't have to do a bunch of nested for loops. And then this is really important. You have to, when we're compiling this HLSL, we have to make sure that we're only compiling this section if we're doing a GPU simulation. Otherwise, things fall apart. And then this section here, or these first two lines here, we're going to figure out the position of the particle in 0 to 1 space relative to the neighbor grid. And then we're also going to get the index, the grid index of our current particle based on its 0 to 1 position. So that's all this is doing. And then we get the num cells, the max neighbors per cell, and we start iterating over all of those index offsets. And then we're iterating over the max neighbors per cell. So the most number of iterations we can ever do for any of these particles is 27 times 15, which is a lot simpler if we're dealing with 4,096 units, right? I'm only working on that little bit of math. And then the next step that we're going to use is figure out what the grid cell offset we're working with. If it's, -1, -1, if we're in 2, 1, 1, -1, -1, -1, now we're in 1, 0, 0. And we figure out and using that value, we can grab the current neighbor index. So that's, I've only got 15, 0, 1, 2, 3, 4, 5, 6, 7, 8, 10. I'm going to store that in this neighbor linear index value, and then I can do this get particle neighbor to get the particle index of that particle. And now I have stuff to work with because I can use the attribute reader to get the position of that particle. And then all we're doing down here is checking the distance between the particles. If it's within our sort of overlap range, and we're going to start working with it, we get a normalized vector away from the other particle. We push it away, increment the neighbor count value over here, and then all we do is just average the repulsive force by the number of neighbors. So if you've got 10 neighbors, we've accumulated this sort of direction away from everybody. We're going to average that together and then multiply it by the repulsive force strength, and we'll get to this last line in the next step. Cool. So I will set up all of put that in the right spot, and then I will set up I dragged this position value over here, and I needed to make sure it's the particle position. Easy. Almost messed up. So then we're going to grab the neighbor grid 3D from our emitter, and then we're going to get our attribute reader. Here we go. And then our world 2 grid unit. So that's going to get everything together. And you can see these particles are already kind of fighting to be where they want to go. And I'm going to make that even worse for them by making them all go toward the center. So because I set the repulsive force really, really high so that you could see it, they're all trying to get to 0, 0, 0, and they keep bumping into each other because I set their overlaps really, really high, right? So that's all we really needed there. Here's what that looks like with 64 particles. And you can see things get a little hectic, right? So I'm doing an interesting calculation in Niagara, and I can do some really cool stuff with it. And again, that's basically the same thing that's going on in our giant example. They're all trying to go to their goal positions, and they're all kind of pushing each other out of the way. But I lowered the overlap value in the forces here because I thought these guys might be a little nicer to each other. But you can see, like, as I move these units away, these guys are like, oh, okay, well, I'll give you space. I'll give you a little space, right? Cool. So we really quickly learned how to use Neighbor Grid 3D, how we can use the built-in modules, right? Initialize Neighbor Grid 3D, populate Neighbor Grid 3D, and how we can access positions of other particles from within, from a current particle evaluation. We can make those repel each other. So now, as I take a sip of water, now let's talk about how we can efficiently store state information, any kind of arbitrary information about our particles, our units, whatever thing we are operating on in Niagara, into a single float. Because here's the thing. Colors are just proportions of red, green, and blue light, right? And those proportions are represented by numbers, 83% red, 23% green, 100% blue. Now here's the thing about floating point, 32-bit floating point numbers, is 32-bit floating point numbers are actually 32 booleans wearing a trench coat. Thank you for sticking with me on that one. So why go through all this effort, right? It's a memory efficiency thing, right? I've got one number. So let's say, we want to, in our material, know about the number of neighbors that we've got around us, right? How many people are overlapping? How many particles are overlapping us? Maybe I want to know the current index grid cell that it's in for whatever reason. And maybe it's a distance to its goal position, right? And we could use dynamic material parameters for that in Niagara and just pass that through as about 5 different 32-bit floats, which ends up being like 160 bits. And if we multiply that out by our 4,000 units, that's like 600,000 bits, y'all, which is almost 600 bytes. Okay, I know that that's not like huge given the machine that I've got under this desk, but maybe it's not about memory efficiency, it's about efficient use of the channels of data that's available to us. You only have 4 UV channels with Nanite. You only have 32 custom primitive data floats and per instance custom data floats, maybe and 16 dynamic material parameters. Maybe you need to be efficient about the channels that you have available to you. So I need to pack more information into a UV or a dynamic material parameter to make room for the other stuff, because I don't actually need all of the precision of a full 32-bit float to store the index, to store the number of max neighbors, because the maximum number of neighbors is only 15. So let's jump into a material, and I'm going to show you a really handy node to help you conceptualize how all of this stuff works. So I set this up real quick. I've just got a custom expression returning a float into the debug binary values float. So we're all probably familiar, I hope, with debug scalar values, right? So this is just going to show me what that float number is. These are very handy for debugging stuff in materials all the time. And then if you have an interest in doing what I'm about to show you, this debug binary values float is really, really handy. So we're going to zoom in on that so we can see that. And then we're going to zoom in over here so we can see that. All right. So instead of returning 1.0, maybe I have an unsigned integer called value equals 0. And then I want to, because we're going to use a float anyways, so we're going to kind of think about float space. So what I can do is, instead of returning the value converted to a float with just like a float like this, I want the bits of the value to be treated as a float, which is a slightly different thing. So we're just going to return that as float, super handy. So we'll return value as float. And of course, you know, a value of 0 is 0, but maybe I can use, I don't know, 16 of these bits. So 16 bits gives me about 65,535 steps of information, which is more than enough for me to store a rough approximation of a current particle's position to its goal position, right? And that is very handily represented by the hexadecimal value OXXF, right? So that is my first 16 bits, or if you wanted to, 6,535. 65,535, same thing. I think it's really handy to use these hex values because sometimes the numbers you're going to have to work with are not as convenient as that. So that's our first value. And then, you know, I've got 16 more bits to work with. And I know that the max neighbors per cell is 15, which is actually very conveniently OXF. That's 4 bits. 4 bits times 4 values, neighbors, index X, index Y, index Z, well, that's another 16 bits. But OXF is sitting where I want to store my distance value. So I gotta move that over, which is really easy to do with a couple of double less than operators. I wanna move those bits over, shift those bits over 16 values, and now I've got my 4 bits right here. And now you're thinking, okay, but I got to combine these values together to pack them together, right, before we send everything out. So all we have to do to pack everything together, assuming the starting bits are 0, is an OR equals. So a pipe equals is OR equals OXFFF. And now I've got all of that stuff packed together, but they're not colliding with each other, which is really, really handy. So then we need to unpack these values, which is a little trickier because I need this value, these 4 bits in the right spot, right? So instead of that, what I can do is say value equals, actually we want to go value equals, oh right, I can just shift that over. So value equals value shifted over 16 places. Right? Super easy. So that's the, I've taken my 4 bits from 16 to 20, and I've shifted them over 16, but I also need to mask them out because I'm going to have bits on either side of this that aren't going to play nicely with that. So then I just do an and equals OXF. I want to bracket this in parentheses because I'm always nervous about that. Very liberal with parentheses. So I'm going to mask out. I'm going to say everything on either side of this that's not, you know, up to 15. I want to mask it out, and then I can shift it over So just in case I had something at, say, value equals OXF shifted over 20, right? So I don't have any of these values in the wrong spot. Cool. All right. So that's kind of the basics of how that works. It's a lot to recreate, but I whipped up some shader code that I can include in both Niagara and materials. I should post this on the EDC article that you're going to link to at the end of the show. Give me like an hour and I'll take care of that. So then in the avoidance stage that we've got down here, right, I already have most of the values that I need, right? Index X, Y, Z, and the neighbor count. And then for the sake of time, I'm going to skip over the quantizing the distance, but we can talk about that later. And this is, again, going out as a float value, so then I can just say set dynamic material parameter 1, and then I'm going to use the convert node here because I'm a huge fan of it. So we've got that value coming in. I've got my parameter. That's going to go into the X value. Then I'm going to make another float just so we can zero out everything else. So now I'm taking all of that information that I've got and I'm sending it to the particle's material through the dynamic material parameter channel. And then we can jump back to our particle material over here. And let's just, for the sake of time, I'm going to say, let's grab the dynamic material parameter, and then I know that this is up to 15. And actually, I have already staged for myself a helper function to get the parameters of the sprite. So it's just doing masking and shifting, nothing you haven't seen already. So that gives me my neighbor value, and I know that that neighbor value can go up to 15. And now what I can do is scale the brightness of the particle based on the number of neighbors, right? Maybe I want to have everybody be glowing more the closer they get to each other, but oh, they're running away from each other, and isn't that so sad? And then, yeah, let's go take a look at that. So all of these particles have maybe a few more neighbors than we're expecting, but we can also, as a fun little demo, we can also grab the grid index, right? So that's a float 3 value, and I'm just going to, for the sake of argument, debug float 3 values and send that out. I'm going to add that into emissive so that we can always see that. Okay. Apply and save. And then if this doesn't work, then what I know is that my references were messed up, which they were. Easy. So now we can play an editor. Ooh, and then the other reference was messed up. Live demos, right? Oh, that's the right one. Interesting. So I think that's because based on the grid size and all of that fun stuff, trust me, it works. Because that's how all of this stuff is working. I can prove to you that this works. So the health value, that's in the first 16 bits. I also store, if the unit is selected, that's 1 bit. That's the 30-second bit. And then the animation state, so if I'm idle or if I'm moving, the direction that I'm moving, and I use all of that. I use some of that in the particle system to select which sprite sheet in the flipbook we should be using, and then some of those values then get passed on to the material so that I can draw the unit outlines and all that fun stuff. So cool. It's, again, this is, in my mind, more about being efficient about your channels of data necessarily than the memory, but I think it's a fun trick to keep in your tool belt. So yeah, right, colors are just numbers, and numbers are just bits, and bits can be shifted and operated bitwise, as opposed to, like, you don't have to treat it as an array of 32 floats. You can just treat the thing as itself. All right, so we have arrived at the final little trick that I want to show you today. So let's talk about distance fields. Right, distance fields are basically for any given point in the field. The value at that point is the distance to the nearest surface. And if you've got a signed distance field, the numbers can be positive or negative, where negative numbers denote that you are inside of a surface, and positive numbers represent you being outside of the surface. And we'll use these to make a sort of pseudo screen space mask around our particles. So I did set up a couple of little helpers here. So right, we've got our positions render target. I've already got another render target set up in the material. That's just a 32-bit float render target. and we've got a couple of materials we're going to work with. So we're going to do this in 2 stages. The first thing we're going to do is use the draw material to render target node to create the distance field as that render target. And then in a different material, we're going to sample that render target by transforming its, the world positions into something that makes sense for that distance field. So basically 2 steps. First, draw to the distance field, and then sample the distance field. So in the blueprint, this part is really, really simple, and I've already set it up for us. Every frame, we're going to draw material to render target. And now here's the thing about this is when we do this draw material to render target, that renderer doesn't know anything about the world of the main view that you're rendering. It only knows I'm rendering this material to this quad and that's it. So it doesn't know the camera vector. It doesn't know world position of the thing that you might be sampling it from. So we have to transform the 0 to 1 values of that quad into something that makes sense for our distance field renderer. So what I'm doing on this plane that we're using for the fog of world is I'm sending in the center of the bounds and the extents, and that's what we're going to use to transform our values from 0 to 1 into world space relative to our object here. So here is ignore that, because I knew I was going to start running out of time here. So all I'm taking is our 0 to 1 values, shifting that over a little constant bias scale, scaling it out by the extents of our plane, and then adding in the center. So wherever the center is, we want to move that over. So now if we've got something that's 1,000 by 1,000, the bottom left corner is like -500, -500. The top right corner is 500, 500. And that way, so that's our UV value, if you will. I'm also bringing in the particle positions render target and its texture size. And then over here, because again, this is going to be a lot to type out, I should also put this snippet in the EDC article. So basically we're saying, all right, if I want to sample from the positions render target the exact value, and I don't want to worry about any kind of bilinear filtering, I need to offset my UV ever so slightly for that sample. And then I just initialize some values. I initialize the result. So the maximum value that I would expect to see here is 1. And then I'm going to loop over all of the pixels in the render target, X and Y. And then I get the UV that I should be sampling the position from, which then gives me the XY position of the particle in world space. And then the UV values that we're working with are also in world space. And what we can do to create the sphere distance field, right? I'm just going to use a circle right now. That is just distance between our 2 positions, in UV sample position, minus the radius of the circle that we're working with. And then because I didn't want to deal with numbers that are too high, go back, there we go. I didn't want to deal with numbers that are too high. I'm also going to normalize that to the hit radius. So this is going to give us 1 particle, and we want to combine all of these particles together as we are working. So all we have to do for that is say, just get the minimum value of everything. So result equals min result, and then our new distance field calculation. And then hopefully that compiles. Capitalization gets me every time. There we go. Oh, and another extra parenthesis. I told you I was liberal with parentheses. So we can apply that value, and this is going to draw into our render target. And then actually very conveniently, because of the way that I have contrived this example, we don't actually have to do anything super special for sampling our distance field, because I'm using the bounds of the plane that I'm drawing from to go from 0 to 1 to world space, which means that the distance field is already in 0 to 1 for the thing that I'm sampling it from, which makes this example really, really simple. So all I have to do is remember to set this to linear color, and then pass that out to the opacity mask, and this should mask out the areas around our particles. Okay? There we go. Aha! So we've got all of our particles looping together. They should be all looping together. That's fine. We're just going to drag everything in instead. How do you like that? There we go. Hold P. I wonder why that's not working. Well, in any case, that's also how I'm doing the fog of war. We loved live demos. So yeah, again, this is kind of the same thing that I was showing earlier, and EDC article will have the more correct examples of this. But all of the particle positions are getting written into the distance field, which is our, which we're then using to render the fog of war. And then I just do like a couple of like dithering tricks to do that added effect, right? So we can move everything over there. And there we go. So cool. Actually, didn't go over time on this, right? So I think distance fields are a really powerful trick, and you can do your own things with these distance fields. It is a super deep rabbit hole. If you have ever seen Inigo Quilez's tweets or work, you might start to get an idea of how deep this rabbit hole really goes. I will also call out that there's a bunch of distance field in that example that's not visible on screen because, you know, I've got this giant plane, but we can only see this little part of it, and I will leave it as an exercise to the reader of how we can do that a little bit more efficiently. But right, all we're doing is is transforming 0 to 1 in our UV space into the space that we want to draw our distance field in, so that we can then pull in the world positions of our particles, our distance field shapes, or whatever, we can bring those in. And if you want to get really advanced, when we're writing our positions to that render target, what if we also wrote like parameters of our distance field shape into the alpha value of that render target, right? I don't want to have to sample 2 render targets to get all these parameters. I can be efficient about my data channel use, right? So I'm sure you're a little curious about the results. So in the project that I've got, the way I have it set up, I can interact with about 4,000 units before things start to get challenging on a Galaxy S10. And most of that actually is from the distance field rendering. So I will leave it again as an exercise to the reader on how we can improve that in the future. Jump flooding. If anybody wants to come check it out or talk more about this, again, I guarantee you I will be in the Dev Hub from like 1:30 to 3 tomorrow, but there's also a TV screen with my schedule on it, so you can check that out as well. Okay, so what have we learned today? Well, we learned how we should be building real-time strategy games, and we also learned how we shouldn't, but instead, we learned how we can use Niagara as a compute shader to allow deeper interactions with our particles, how to use the neighbor grid 3D to allow our particles to interact with each other, and then we learned how we can pack a bunch of data into a single float with Bitwise operators, and finally, we learned how to make a simple distance field representation of our particles, and I just remembered why that demo didn't work. So thank you all very much. If you give me 2 seconds, I'm going to go figure out how that works, and then we can get to questions.